Good afternoon, everybody. Let's pick up where we left off. So we had started talking about complex exponentials. Actually, let me backtrack a bit from there. I started talking about some important signals that you're going to become intimate companions with over the semester. And those signals were e to the I omega t and its discrete time counterpart, complex exponentials. There's a bit of a lie there because this is not the most general complex exponential in either discrete time or continuous time. There's a broader class where you have a complex number sitting in front of the t. I'll talk about that a bit either later today or in the next lecture. And the other important signal is the impulse which I drew the discrete time version for you. It's a signal that's 0 everywhere except at n equals 0. This is the discrete time version. It's called the Kronecker delta. Its continuous time counterpart has a lot of mathematical anomalies, but graphically we represent it this way with an arrow at 0. We put a 1, not to denote its height. Its height at 0 is infinite. But the number 1 represents the area under the impulse. This sounds bizarre to you because the width of this object that I've drawn, this arrow, is 0. So how can the width be a number? You can kind of hand wave right now and say, okay, 0 width times infinite height gives me a finite value. But we'll get to that later. But I started discussing what happens in the complex plane with regards to the complex exponential. So let's go there. We had this object, e to the I theta, where theta is a real number. And one of the important properties that we arrived at last time through a power series expansion was that you can write this e to the I theta in terms of cosines and sines. And what was that formula? Cosine theta plus I sine theta. And graphically, we concluded that we are sitting on the unit circle. So I have the imaginary axis, and the real axis and the imaginary axis. I'm sitting on the unit circle. If this is e to the I theta, I represent that, suppose, with an arrow. It's a point on the unit circle whose projection onto the horizontal axis or the real axis is what? Cosine theta. That's its real value, the real part. And its projection onto the imaginary axis is I sine theta. And from this, we came up with I sine theta. Yeah. And from this, we wrote down complex exponential forms for a whole bunch of numbers that sit on the unit circle that you've seen before. For example, the number 1, if I were to write it in terms of a complex exponential, how would I write it? E to the I0, whoops, or e to the I 2 pi, or e to the minus I 2 pi. In general, e to the I 2 pi times an integer. Okay? K here is an integer. Theta is also the angle. I need more colors. Theta is the angle that this point makes with the positive real axis. So let me move this to the other side. And then this angle would be theta. There's always a 2 pi ambiguity with regards to this angle, which we also call the phase of e to the I theta. Theta is the angle or phase of e to the I theta. So what about the number minus 1? E to the I pi, or e to the I 3 pi, e to the minus I pi. In general, e to the I 2k plus 1, some odd integer, times pi. Okay. What about I? E to the I pi over 2 and its equivalents. And minus I will be e to the minus I pi over 2 and its equivalents. Okay. One of the things I want to encourage you to do, in fact, you probably won't be able to survive very well in this class if you don't, is to get used to using pictures, drawing diagrams, and extracting information and drawing inferences by looking at diagrams. If you don't look at, for example, the unit circle, it may be somewhat obscure to you that you can write the number I as e to the I pi over 2. Then it will be only formulaic, because you'd have to go into the Euler's formula at the top and plug in values for theta. Whereas if you look at the picture, it jumps out at you. Okay, so in this course, you should get used to drawing pictures. Or, if we give you pictures, to look at the pictures first and see what you can extract from those pictures. Any questions here? What happened to all you people this morning? Deadbeats. Yeah?
I was wondering, should we think that complex explanation of vectoring a vector space in which the vectors is 1 and I, or is that kind of true?
Very good question. So the question is, should we consider these numbers, these various numbers, as vectors in the complex space? And what did you mean by vector space? Are you referring to the Math 54 interpretation? No, I don't want you to go into the Math 54 variety of interpretation for this. That's an overkill. But you can consider a complex number as a vector in the complex plane. So I pick a number in the complex plane. Okay. It has a real component. It has an imaginary component. And let's call this number z. Okay? That's the number z. So I can write z as a plus ib. That's straightforward. This is the Cartesian representation. Cartesian representation. of the complex number. You keep hearing my breaths. Okay. There is another way to think about this. Of course, you can always draw the vector. In fact, when you're trying to add complex numbers, you may want to keep the vector interpretation in mind. Because if I have two vectors, z, and let's call this one y, and I want to add these two, how would you do it? From high school. Parallelogram rule. You draw a parallel and equal in length to this guy, and you draw another parallel, and that would be the sum total. So in that sense, looking at a complex number as a vector in the complex plane is very helpful. It gives you a picture. Another interpretation is what we call the polar form. You look at the angle that the complex number z makes with the positive horizontal axis, the positive real axis, and you look at its length and call that capital R. So you write z as r e to the I theta. In the previous picture, what was r? Huh? 1, because you were sitting on the unit circle. All the points on the unit circle have the radius 1, have a distant 1 from the origin. This is my 0. Right? But there's nothing that restricts you to the unit circle when you're talking about complex numbers. You can wander off anywhere. So this is called a polar representation. And there's an important distinction between, that's 10 points off your midterm. There's an important distinction between these two. The Cartesian representation is unique. This is unique. But the polar representation is not unique. Why? Huh? It's the ambiguity in the angle theta. So because of ambiguity in theta. I have a student in E120 who gets upset when I don't close the parentheses. He shall remain nameless. This is being filmed, man. You want to get me in trouble? Now, can you tell me what the relationship is between r, theta, a, and b? Can you figure out the radius from the Cartesian coordinates? This is now high school stuff. Because it's all about Euclidean vectors, right? You don't have to know anything about complex numbers to do this. The distance from the tip of this vector to the origin, if this is a and this is, if this distance, the magnitude of this distance is b, what is it? Square root a squared plus b squared. And what about theta? Arctangent b over a. And to the extent that arctangent has ambiguity, your theta has the ambiguity. Okay? What about the other way? How do you relate a and b to r and theta? That depends on whether I write it with a small a or a capital A. We're not going to get hung up on those things. Arctangent is a periodic function. If you plot it, you have these replications that are distant from each other by 2 pi. So depending on which 2 pi interval you pick, you're going to get a different answer. But don't get hung up on this. There's a principal arctangent that's usually defined written with a capital A. Not universally so, but usually in textbooks it's written with a capital A. And that's between minus pi and pi, or minus whatever. They pick one of those principal intervals, and they define it that way. But the 2 pi ambiguity in the angle permeates throughout. And that's actually sometimes good, because you get to pick which 2 pi interval is easier to write equations for and expressions for. Okay, what about A? R cosine theta. Yeah, because the number z is sitting on a circle of radius r. And when I project onto the real axis, when I project this number onto the real axis, it's this r times the cosine of this angle. And B is r sine theta. So these are all the relationships that you can infer by simply looking at the picture in the complex plane. That's why I keep insisting, look at pictures, draw diagrams. You get a lot out of it. All right. So does this, you asked me the question about vectors? Does this pretty much cover it for you? Okay. Now, we wrote down the equation that relates the complex exponential with sine and cosine. And this, remember, we called Euler's formula. Can you come up with a scheme or with an expression that relates cosine to the complex exponential? That's what I want you to talk to your neighbor about for the next 2-3 minutes. Try to come up with an expression that relates cosine with the complex exponential and relates the sine to the complex exponential. And I'll give you a hint. If e to the I theta, so this is my unit circle, e to the I theta is sitting here. E to the I theta. This is the unit circle. Okay? E to the minus I theta sits here. What is the expression in terms of cosine and sine for e to the minus I theta? Figure that out, and then use the two equations to come up with an expression for cosine in terms of the complex exponential only. So I don't want to see a sine in that expression. I want you to write the cosine in terms of the complex exponentials, and I want you to write the sine in terms of the complex exponentials. All right? Go for it. right. Meatball. It's your day. First day on the job. You want to go for it yourself, or do you want to pick somebody? Okay. E to the minus I theta. In terms of cosine and sine, what do you got?
Oh, maybe I give it to someone else. I solved for cosine theta, not for e to the minus I theta.
Well, you must have figured this out before you went to the other one.
Cosine theta minus I sine theta.
Cosine theta minus I sine theta. Minus I sine theta. And how do you find it on the diagram? How do you know that this is a minus? There's a minus sign here. Well, this is the vertical axis. If this had been I sine theta, then this is clearly minus I sine theta. Right? Okay, now you have these two equations. Tell me how you're going to get cosine. Don't give me the final expression. Tell me how you get there. You added them, okay? So, I'm going to make you a celebrity. Meatball says, add e to the I theta no, not end of quote yet. And e to the minus I theta unquote. All right, now what? Let's add them. What do you get? Mm-hmm. So cosine theta is? This is one of those expressions you're going to get so intimately close to, you're either going to love or you're going to hate. Some people call this the inverse Euler's formula. I don't care what you call it, as long as you know what it is. Cosine involves a complex exponential and its negative argument complex exponential divided by 2. All right, let's pass the torch to somebody else, Meatball, for the sine. No. See, the way we keep them on their toes is that we don't ask for volunteers. We pick.
Oh, we just pick something?
Yeah.
How about paper airplanes next time? How about somebody over there? Right there, sitting there with a finger in his mouth.
Now you know why I don't do this myself. Okay, thumb sucker. Who is it?
Who's searching over there?
Third
Third row.
row.
Fifth on the right. Come on, guys. Okay, so now that you're just...
And you are?
Sammer.
Samer. Okay, Samer.
Okay, instead of adding
Mm-hmm.
two equations,
Mm-hmm.
just subtract them.
Samer with an I or an E? E to the I theta minus, actually, let's write it down. And you're saying do what?
Instead of adding those two equations, we're going to subtract.
Okay, subtract. And what do you get?
E to I theta minus e to the negative I theta equals 2I sine theta.
The cosines now cancel. And so now you have an expression for sine in terms of the complex exponential. Please don't forget this annoying I in the denominator for sine. Okay? Together with Euler's formula, these two expressions, you're going to just have to have at the tips of your fingers for momentary recall or instantaneous recall. These will play an important part. Any questions so far? So we're playing around with the geometry of the complex plane to learn a few things about complex exponentials. I haven't turned the picture into a dynamic picture yet. I haven't introduced the element of time. I'm going to do that next. So far, we just have a parameter theta with which we play. We're talking about a point on the complex plane. Now I want to give this point motion. So let's introduce dynamics, or time evolution. This is not the controversial political religious evolution. This simply means progression in time, or as things evolve with time. As the particle moves in time. The nature of the particle doesn't change. It doesn't go from a chimpanzee to a human. I'm not getting there. I'm just talking about, what's that? Oh, okay, fine. Take a break. We'll come back after a break. Okay, let's resume. So we're now introducing the element of time. Oh, actually, before I go there, I've been asked several times where you turn in your homework. In the student lounge on the second floor of Corey, there are drop boxes. Just make sure you don't drop it into the EE 120 box. We sometimes get cross-pollination, and it creates a logistical problem. So there should be a box in the student lounge on the second floor of Corey. That's where you turn in your homework. And the other announcement is that we have been given 10 Evans for the 23rd of September for the exam, but I've objected because it's too cramped. I want a bigger room where you can sit spaced apart and have and be comfortable. So I haven't heard back yet, but we may have to just bite the bullet and take what they give us, because the date is more important than the classroom at this point. I want you to have a data point as to where you stand in the course before drop date. And the last announcement that I just remembered is we are going to meet outside for those of you who are not in a group yet, and we try to do some matchmaking. So this way you have some study buddies to work with. And then after a few weeks, we'll revisit the groupings and see who needs to shift and so on. But by then, you probably have met other people and may do the shifting yourself. But in any event, I'll ping you again at that time and see how things are going. Okay, so now we're introducing the element of time. In other words, we're looking at the complex exponential e to the I omega t, where omega is some constant. And we want to see how this function behaves. A good way to think about this is as the location of a particle on the complex plane. One thing you do know about this is that no matter what the time is, this particle always sits on the unit circle. It does not leave the unit circle. Just like e to the I theta, except this theta. So you can think of this as e to the I theta as a function of time. Okay? So theta of t is omega t. I'm making theta time dependent. That angle that it makes with the real axis is not time dependent. What happens now? Well, let's go back to what you know about, or what you should know. The known knowns from your basic math class. You've seen the regular exponential before. Some of its defining characteristics are that, first of all, at time 0, its value is 1. And when you differentiate it with respect to time, you get itself back. Now, what if I modify this and look at e to the alpha t, where alpha is a real number? G of 0 is still 1. And the derivative of g, by the way, we usually use in this class and in a lot of engineering courses the dot notation whenever we differentiate with respect to time. So the dot on top of the function denotes the derivative of the function with respect to time. And similarly here, I'll use g dot of t to denote the derivative of g with respect to time. And now what do you get? Alpha e to the alpha t. Okay? Now, when we expand our scope and allow this alpha, whatever is multiplying t, to become a complex or imaginary number, when we go to the complex plane, we will insist on same properties for the complex exponential, let's say e to the I t. F at 0 is 1. And f dot is I times what? E to the I t. In other words, it's I times f of t. Now, before we go forward, we need to understand what it means when we multiply a complex number by I. I'm going to give you a minute to think about that, and then we'll hash it out. What does it mean when you multiply a complex number by I? And this is where I want you to draw a diagram. Just pick a complex number that you like. Multiply it by I, and draw both numbers on the complex plane, and see what you get. So I'm going to put that as a question. What does it mean to By the way, I assume that when you're talking to your neighbors, by now you've introduced yourselves to each other, because I want you to know as many people in the class as possible. Okay, are we there yet? Samer. Samer gets to pick the next victim.
This row all the way to the leftmost person on this row.
Leftmost person on Samer's row. You're it. Wait. These people don't know who you are. Faraz. Okay, Faraz. By how much? Pi over 2. Okay, so Faraz says that it rotates the point counterclockwise by pi over 2, by 90 degrees. Does that jive with what you had? Okay. So Faraz, give me an example. Just pick a number on the complex plane. Keep it reasonably simple. Now let's do it. I can give you a number, and then you can tell me what it is. I'll give you the number 1 plus I. multiply this number by I. What's the angle? 45 degrees. Or pi over 4. And what's the radius? It's root 2. So, in other words, the polar representation of this number is e to the I pi over 4 times root 2. Okay? Now multiply this number by I. So IZ is what? Give it to me in Cartesian first. No, you're still converting to exponentials. I want you to multiply I and 1 plus I. Negative 1 plus I. Okay? How do I draw that? Which quadrant is it sitting in? Second one. And how do I draw it? Okay, your hand gesture shows you know what you're talking about. And what's this number here? Negative 1. And this is? I. So this is IZ, which is negative 1 plus I. Now, the other method you were doing it in, you were using, was by saying I is equal to what? E to the I pi over 2. And Z is, in general, well, let's keep it specific to our number here, times that. So IZ is what? Give it to me in polar form. Square root of 2. I pi over 2. You need to be a little louder, Faraz. So notice what happened to the angle. You added a pi over 2 to the angle. Every time you multiply a complex number by I, you simply rotate wherever it's sitting by pi over 2. And this is true for any z. So if z is equal to r e to the I theta, then iz is r e to the I theta plus pi over 2. Okay? So this was a detour. Now let's go back to the original question. We've noticed that the time derivative of e to the it is I times e to the it. In other words, the derivative of that, or the velocity of that particle, is I times the displacement of that particle. Let's go back to this board. And see what's going on. So we said, let's look at f of t as the position or displacement of the particle. F dot, which we define as the derivative of f with respect to t. This means it's defined as definition. Is we've discovered is I times f of t. Okay? In other words, the velocity, or this is the velocity of the particle. So here we have a particle. Let's say in general, it's at time equals 0, it starts here. And then it carves out a trajectory for itself. So this is f of t. at some point, and let's say this is, well, in our case, it started at 1. At some arbitrary point in time, its position is f of t. If I were to draw its displacement, its velocity, how would I draw it? Huh? Tangent to the curve at that point. In which direction? This way or this way? This way, because it makes a positive 90-degree angle. And what's the length of this vector? The same as the displacement length. Okay? Because if I take the magnitude of this, I take the magnitude of this, and the magnitude of I is simply 1. So the magnitude of the velocity is the magnitude of I times f of t, which is the magnitude of the product is the product of the magnitudes. And if you're not comfortable with that yet, if you haven't hit Appendix B yet, which you should have by now, and the magnitude of I is 1. So the vector that represents the velocity of the particle makes a 90-degree angle with the vector that this diagram is not in a good place. Let me move it to a less cluttered location. So this is my particle at time 0. Let's say it carves out a trajectory. At time t, this is f of t. And we're saying f dot of t is the tangent to that point, is the tangent to the curve at that point. Its direction is 90 degrees counterclockwise from the direction of the position of the particle. And its magnitude, its length, is exactly equal to the length of the displacement. Okay? Now here's my question to you. What is the set of points, what is the trajectory that guarantees these two conditions for all time? You start off on the unit circle here. The initial velocity is upward because it makes a 90-degree angle to the initial position or displacement. And this relationship between the velocity and the displacement is preserved as time goes toward infinity. What kind of a curve satisfies both those properties? A circle. So a circle is where, so this is where the particle is initially, and this is the initial displacement. So this is f of 0, and this is f dot of 0. Then you go forward in time, and I'm exaggerating the epsilon angular displacement. And this relationship, actually the fact that this is equal to this vector is not the main point. The main point is that the velocity, which is the tangent to the trajectory, must be orthogonal to, perpendicular to, the displacement throughout time. And the only trajectory that has that property is the circle. So the circle is the locus of points for which f dot of t is orthogonal to f of t. So this simply means orthogonal or perpendicular to. Locus means a set of points that share a particular geometric property, or not necessarily geometric, but a certain property. So the particle moves around the unit circle. Yeah?
Would some sort of spiral work?
Why would a spiral not work? A velocity, well, there are different ways you can argue it. You have. Well, one way you can argue it is that you're going to have to return to the same place after some time because of the 2 pi ambiguity in the phase. You have to return to the same place after some time. A spiral doesn't have that property. And then you had another argument.
The velocity must have a radial component if it's a spiral.
The velocity must have a radial component if it's a spiral. And it can't be orthogonal to or perpendicular to the displacement. So if this is going to be a spiral in, for example, then there is a component of the velocity that projects radially inward onto the displacement, which violates the perpendicularity. Okay? Very good. Okay, so now that we've introduced the element of time, we are seeing a particle that starts off on the unit circle and goes around the unit circle. What is the contribution of omega? Omega. It's the speed. It just sets the rate at which this particle goes around the circle. If omega is positive, actually I want to write this argument so that those of you taking notes can. A spiral won't do because it necessitates a radial component for the velocity, violating its orthogonality. With the displacement. Okay. Yeah.
How about a particle making loops as it goes around the 3D space?
What kind of a loop? Anytime you move away from the circle, you have a radial component on your velocity. So any strange loop shape, the moment the radius changes from one instance to another, you have a radial component along the velocity, either inward or outward. And that violates the orthogonality. Okay, so with e to the I omega t, omega, the constant omega, determines the rate at which the particle traverses the unit circle. Okay? If omega is greater than 0, what's the direction of travel? counterclockwise. And when omega is less than 0, it's clockwise. And when omega is equal to 0, it's doesn't move, a stationary point. Stationary particle. Okay. Omega equals 2 pi. How long does it take for the particle to go around the circle? Pardon me? 1 second. You want 1 second to find the answer? Or is that the answer? Omega equals 2 pi. How long does it take to go around the circle? I've already given you 1 second. Who's on first? That's exactly what I wanted to hear. 1 second to go around that circle. Okay. And this would, so the units for omega is radians per second. And this is called the angular frequency. Angular frequency. So omega is angular frequency. Its relationship to the frequency that you're more familiar with coming into this course, namely f, which is the cyclic frequency. And what's the unit of the cyclic frequency? Hertz, or cycles per second. You just told me that when omega is equal to 2 pi, the particle goes 1 cycle around the circle. So what's the frequency? Cyclical frequency corresponding to 2 pi radians per second. 1 hertz. So this is equal to this I shouldn't say equal to. This corresponds to f equals 1 hertz. And the relationship between these two is omega equals 2 pi f. F is cycles per second. 2 pi is radians per cycle. So you get radians per second. Let's write that explicitly. 2 pi is radians per cycle. F is cycles per second. And so when you multiply them, you get radians per second. Now, why is all this so important? Remember, we said e to the I theta was cosine theta plus I sine theta. So e to the I omega t is cosine omega t plus I sine omega t. You also had a relationship between cosine and the complex exponential. So cosine omega t is e to the I omega t plus or minus e to the negative I omega t divided by 2 or 2i? 2. And the sine is e to the I omega t plus or minus what? E to the minus I omega t divided by 2i. Okay? Now let's go back to e to the I omega t. That's a particle rotating around the unit circle. We said the frequency of e to the I omega t has frequency omega radians per second. It's a single frequency function. It's simply going around the unit circle at the rate omega radians per second. And I should say here, it's the only frequency present in e to the I omega t. Okay, so e to the I omega t is the prototypical representation of a single frequency function. How many frequencies are in the cosine? What do you think? One. Two. Well, what about the rest of you? I don't know and I don't care. You can bark all day and bark all night. I don't care. Okay, cosine omega t has how many complex exponentials in it? What's the frequency of the first complex exponential? Omega. What's the frequency of the next complex exponential? Negative omega. What's the difference between omega and negative omega? Huh? Direction of the rotation. So positive frequencies correspond to counterclockwise rotations. Negative frequencies correspond to clockwise rotations. And there's a big distinction. The particle is traveling in different ways. So a cosine has frequency omega and minus omega, and so does the sine. Omega and minus omega. So we've already talked about positive and negative frequencies and how they're distinct. So a cosine is not a pure signal in the sense that it contains a single frequency. It does not. It contains two frequencies. And since we're running out of time, I want to show you some Java applets. These are all on the Ptolemy website.